I will talk about the instrument intercomparison. Some of you might have heard some of the stuff before. Not that much have changed, but maybe some new aspects came in. And I presented, of course, on behalf of the group who actually run the intercomparison, Thanos, Steve, Vlad, Craig, Ute, and of course, many, many, many more. This was more a community effort to really get this done. Let's start with why did we even do the intercomparison? So again, this was motivated from the ICOS network, from ICOS Oceans. ICOS Oceans is a heterogeneous network of more than 25 stations. If you look with detail in this map on the right-hand side, you will figure out it's not totally up to date. However, it gives you a good impression of what the ICOS Ocean network is doing. So a lot of ship lines, these are the red lines, and a lot of fixed ocean stations. These are the blue pins. So, and as I said, it's a network of ships, the SOOP lines and fixed ocean stations, which of course use different instrumentation, not only between the platform types, so SOOP and FOS, but also within the network, we don't have a standard instrumentation. We have a standard output that the instrumentation should give. In addition, new instruments are coming on the market, so we also would like how do they compare and fit into the ICOS network, and also new platforms become available that are able to carry different kind of instruments. I mean, at the end of the day, we are interested in the surface ocean CO2 measurements and don't care that much, if you can say it like that, where they come from. But of course, we want to know how do all these different measurements fit together. So this was the initial question. And how do we fit into the global context? And if we talk about the global context, then SOCAT comes into mind, the Surface Ocean CO2 Atlas, which is a global initiative where everyone basically submits their data once a year, only surface ocean pCO2 data, and there will happen a secondary QC, and the secondary QC ends with a quality flag, and they are here in this bluish box. So the quality flags are B, C, and E, translating to an uncertainty better than 2, 5, and 10 microatmospheres pCO2. If you wonder about the A, this just means if you have two data sets that have a B and they cross each other and compare very well, then they get a something like a B star. However, but this 2, 5, and 10 we might want to keep in mind for the rest of the slides. So this is how everything started, how we started thinking about it. We were focusing on surface applications. Oh no, let's say so we were looking for a facility that actually can do this. We were looking around and ended doing this at Vlis in Belgium at the Marine Station Oostende. And here on the upper picture you see the Marine Station Oostende with the warehouses, and this one warehouse has a temperature controlled room in there. And down here you see a drawing sketch where we try to fit everything in with 3 water tanks, each 5 cubic meter. And this is how we envisioned to set everything up, some instruments in the tank and underway instruments around on the platform. So we use the submersible pump in one of these tanks to feed the water to all the different underway instruments. And as I said, the submersible instruments and the surface instruments were put into this tank. We used this 5 cubic meter tank with natural seawater coming from the North Sea with the heat exchanger, so we could adjust the temperature of the water. And then we were using acid and base to actually adjust the pCO2. When we did this, we allowed, of course, time for the changes and for instruments to adjust to the new conditions, so that we did not want to see how instruments react to sudden changes. We wanted to see how instruments compare in more or less stable conditions where the change rate was very low. We had 5 calibrated temperature sensors distributed in the whole tank to at least check for physical homogeneity, and we used 6 reference gases, or 2 sets of 6 reference gases calibrated by the ICOS calibration lab, ranging from 0 to 800 ppm, to calibrate CO2 sensors that were in this instruments. We also asked every group to draft something like a quick start guide. So a quick start guide that we understood as guideline for successful deployment. It should not be a manual because we all know no one reads manuals, but it should be a quick, short version of the manual defining what steps need to be done for a successful deployment, because what we wanted to avoid this blaming and shaming game that we all know. Either the manufacturers blame the scientists that they didn't deploy the instrument right, or the scientists blame the manufacturers that they didn't give the right instructions. And one goal was to have this quick start guide, use it during the intercomparison, and maybe improve it so that at the end we have agreed conditions. Again, a little bit to the history, maybe why we did it the way we did it, because it might not be totally clear. So it was initially planned for 2019-2020 as an ICOS internal pCO2 instrument intercomparison with 5 to 7 instruments, something this was the order. Somehow the attention grew and it got internationally recognized, and we ended up with 27 instruments. Some of them were the same type of instruments, not 27 different type of instruments, maybe like 20 different types, but in total 27 instruments that wanted to participate at this intercomparison. But then, as you might remember, this guy hit us all, and it could not happen in 2020. So we decided to postpone it to 2021. So we started a new attempt for summer 2021, and all groups got ready to come to Ostend to do the intercomparison. And this guy was on there again, even in the summertime. So there was a question, do we postpone it again to 2022, which was definitely not an option, because the funding for this intercomparison needed to be spent by the end of 2021. It was funding from Norway, so there was no way to postpone it. So we decided to run it with a small team, and here you see the team. So the 7.5 people, the half people, Hannelore there in the front, in the middle. She doesn't have a beer belly. That's her little daughter who kind of participated in the intercomparison. And then in the front, you see even Thanos with the typical masks that you had to wear at this time. So that was basically the team that ran it on site. And all the other groups didn't bail out. They agreed to send us their instruments. And yeah, this is how it looked like. Part of the instrument got sent to Kiel and fitted in one truck. The other part of the instruments were sent to Ostend. What would science be without black pili cases? And this is an impression of the room before we started putting in the instruments. So here under the wooden construction here, you see the tank. That's the tank, and we built this frame to install all the submersible sensors. And this is then basically more or less the same picture after all the instruments were installed. So around the tank, you see all the underway equipment, and back here hanging at all the ropes were the submersible instruments. So all the 27 instruments were divided into 4 groups, a little bit based on application. So we had underway systems that are typically installed on soup lines or research vessels, and we divided this group in the membrane equilibration and air-water equilibration to account for the different mechanistics. Then we had a group of instruments that is normally used on buoys or surface vehicles. We call it surface instrument. And then there were instruments that are used on moorings that can be submerged completely underwater. Up here, we will not go into detail, the sketch of all the instruments, how they were deployed in the tank, and this picture we know here. And then we changed the temperature during the experiment, as I said, and the pCO2, and we defined 6 intervals, 6 different intervals with different pCO2 and temperatures, where the pCO2 was changing slow enough to call it stable, to actually have it as an intercomparison interval. As I said, we had these 5 calibrated temperature sensors to ensure homogeneity, or at least to track it. And now we can say, yes, it was well mixed, the tank. We had the 6 reference gases. And down here you see the water flow diagram. So we had 3 circuits where we needed to connect the instruments. It was a little bit of a brain exercise to do it kind of in the right way. And the gas connections were a little bit even more challenging to distribute the right gas concentrations at the right time to the right instruments. But we managed. All instruments got water and all instruments got the gases that they needed. And let's jump in the results. So what we see here is basically the pCO2 of the intercomparison reference. So if we talk about reference, what did we use as a reference? There is nothing like a reference material or whatever for surface ocean pCO2 measurements. What we did, we used the average pCO2 of 3 pCO2 instruments that followed community agreed methods and that agreed within 2 microatmospheres during most of the time, meaning more than 90% of the intercomparison. And the color scheme on the upper on the plot here is basically how many instruments we used to create this average value. What you see here is the time of the intercomparison and this shaded areas where the times that we defined as stable enough to be used for comparison. And this is, so to say, then the pCO2 record of the whole exercise. So it started here, and then one instrument was connected after the other, pCO2 still in the room conditions. And then we started to lower it down to something like 250 and went up to something like 800 and did this several times. And again, in these areas here are different conditions ranging from low pCO2 and low SST to high pCO2 and high SST and all kind of combinations in between. So all instruments that we had, all 27, were compared against the intercomparison reference for each interval. And so for each interval and each instrument, we calculated the average difference between the intercomparison reference and of course the standard deviation. And this average difference can be seen as a bias of the instrument, and the standard deviation maybe as a noise. If we look now at the next figures, we're getting closer to the real figures, just the auxiliary conditions here. You see here the atmospheric pressure, salinity, water temperature, and air temperature. Okay, atmospheric pressure, you can only do so much against it. The water salinity is the red line here. And you see in the first half, it was around 31, and then it was 34. This was due to a water exchange that had to happen in the middle of the experiment. And we used natural seawater, so we had to take what we get. You see the water temperature in yellow, it really ranged from 10 to up to 30 degrees. And we also tried to alter the air temperature. This went only in a smaller range, only from between 14 and 24 degrees. But I remember Vlad complaining when we had 14 degrees in the room when it was nice and warm outside. The results are published since last year in LNO methods. Here you see the DOI, but I guess you can just Google it and find it. And this, I guess, more or less the main plots of the publication. And before we even start looking into the detail, what I really want to point out here, and I'm very, very thankful to all the colleagues and companies and institutions here. What you see here, you really see the names of all the 27 instruments. So it was not an anonymous intercomparison from the beginning on. Everyone who wanted to join, we agreed on that we will publish the results with instrument names so that we know what we're talking about. And this worked very well. It was really a community effort. It was a nice discussion that we had there, and I think it's worthwhile to point this out. However, on the left-hand side, you see the average difference. On the right-hand side, you see the standard deviation, and we will not go to every single bar, but on the y-axis, you see here all the instruments. On the x-axis, you see the difference in pCO2 between the reference value and each instrument in microatmospheres. And this is grouped in these 4 groups. And the top group is the instruments that are normally used for buoys and autonomous platforms. Then underway measurements with air-water equilibration, underway with membrane systems, and the submersible is the group below. And the different colors of the color bars are the 6 different conditions that I described before that we had. And then you can see that even that instruments responded differently to different conditions, and the surface instruments basically stay within this 5 microatmosphere limit, most of the time even in the 2. Same as here for the underway air-water equilibration systems. You just can see some instruments underestimate. For the membrane systems, the spread is a little bit bigger, and so it is for the submersible instruments. So the bias here is clear that on air-water systems work a little bit clearer or better than the membrane systems. But of course, they're also a little bit more elaborate. Let's not forget that. The good news, I guess, on the right-hand side, if we interpret the standard deviation of this average differences as a noise, then we can say most of the instruments actually stay within the 2 microatmospheres repeatability, so that actually we do not have a problem with a random error. And this is systems, they all measure precise, but maybe wrong, but a little bit off. So I guess that's the biggest take-home message. Looking at this, of course, you already put a 1, 2, 3 or a gold medal or whatever on it, but we really want to strive again the point that this is not to be seen as a ranking. I mean, of course, some instruments behave better than others, but this is also be seen as a learning curve. And one should not forget that there are instruments that you put on a table, you connect it to power, you connect water, and you go. And there are instruments where you need really experts to set them up to get the right results. So I think that's something that needs to get balanced and that we did not tackle in detail during this exercise here. Some outcomes from this exercise. So really some companies took it serious, they looked at the results and said, we are not happy, or with some things we are happy as our instruments function, they function within the specs, so good. And others said, no, we are not happy, we want to improve. So that's very nice. There is some movement in the manufacturer community. But also the results have an impact. So the so-called cookbook revision from last year changed the flags for membrane-based systems. They normally could get a flag of C, but SOCAT decided that on membrane-based systems cannot get a flag better than E, so better than 10 microatmospheres. The reason is looking at the results from the intercomparison shows that we do not have an objective tool to evaluate the membrane-based sensors to know when they compare well and when not. This might sound very harsh, of course, but on the other hand, it also shows once we have an objective tool, once we understand better how to measure the quality of the systems, this decision will change again. But for now, we do not have an objective tool. And maybe to show it a little bit in more detail, this is just a zoom into the underway membrane systems for the mean pCO2 difference. And here you see the 8 different instruments. Again, now the names now they don't matter. But instrument 2, 3, and 4, and 6, 7, 8 were basically the same instrument. I mean, so 2, 3, and 4 is the same instrument, and 6, 7, 8 is a different type, but the same instrument. And you see that even within the groups of the same instruments, they do not always agree into the same direction. And this was the reason why SOCAT decided, as long as we do not have an objective measure, they will not receive a flag C, but E. So this intercomparison can have an impact. This might now sound like a negative impact, but I guess it also is a good motivator to understand better the instruments we have, and it was a good exercise to point this progress out. Some more take-home messages. The surface ocean pCO2 measurements are still not trivial. Even if the instruments might sometimes look trivial, but understanding the output of the instrument is very important. Air-water equilibration shows a better agreement than membrane equilibration systems, but all instruments, doesn't matter which type of equilibration, at high pCO2 and high temperatures, they start being a little bit off. So the major issues that we saw here is the equilibration itself. So if you really look into the detailed data set, you see for some instruments long tailing after calibrations or whatever. And one low-hanging fruit, I would say temperature sensors. So we even at this intercomparison, we had instruments with not calibrated temperature sensors. They were off by 0.2 or 0.3 degrees Celsius, which is a measurable impact on the final pCO2. So I think we can just make the pledge, please calibrate your temperature sensors. That's very important. Same, of course, is true for salinity and pressure sensors, but basically make sure that at least the parts you're using for your measurements are in good shape. I mean, we had it during the intercomparison that systems were off, and we could correct it by just recalibrating temperature sensors. It might also show the need for regular intercomparisons to evaluate what we have in the community and what new developments brought. Don't want to say but I mean, it needs to be kept in mind that this was a major exercise and it needs substantial resources to run it in that shape. However, if you want to look into the details, that I said, the data set is available at the ICOS Carbon portal. Here's the DOI, or again, you find it at the Carbon portal. You can download it. Maybe don't use your phone. It's 1.4 gigabytes, the whole data set. What you will get are the scripts that we ran that we used to do the intercomparison. They're MATLAB. Sorry, I'm an old man. Can't learn anything new anymore. You find a folder with the results. It's basically the instruments process data and the combined file that we use to produce all the plots that are in the publication. And you find a folder called Lab Books, which has the instruments raw data and some kind of lab journals. Might be a strong word, lab journal, but basically the notes that we took for each instrument. And the so-called quick start guides, which include a short description of instrument and data processing for all the instruments. So it's also a nice resource to start with if you look into the instruments. It also needs to be mentioned the data set is not used to its full potential yet. So I just welcome everyone to get the data and look into the details. They're, as I said, they're publicly available. You are more than welcome to do that. Just some maybe appetizers here. This is a more detailed plot from the whole intercomparison. You see again the 6 intervals and the shaded areas. And this is for the underway air water equilibration systems. And even for, so here you see for the light blue system, sometimes it's above the 0, sometimes under. So I think there's a lot of more information in this data set that we did not investigate in this publication here. If you look into the membrane systems, so it's basically the same plot, but with the underway membrane systems, there's even the spread is higher and there's a lot of information in there. So why do you have this little step here? So we did not investigate this at all. We did not have the time, man and woman power to look into the detail. But again, the data are there. Everyone is welcome to look into the details, and I would appreciate if this even happens. So just to say, there's way more to do, and the data are there. Now, my last words, looking a little bit into the future, maybe first looking back and then into the future. So the 21 intercomparison was conducted under lab conditions using coastal water, which was criticized by certain groups. So this can be done better. And it was run by a small team, which had some advantages, but of course also some disadvantages. So maybe sometimes the expert knowledge of some people were missing in this team, even if we had daily meetings with the whole group. But again, yeah, we were only a few people on site. Ideas for follow-up intercomparison should be based on a research vessel. Then we can do it under real-time conditions, but also real environmental conditions, covering maybe a wide range. If we stick to the Atlantic, something from the lab sea to the tropics, different temperatures, different salinities, different biogeochemical provinces. And the nice thing there, you could also run a full characterization of the carbonate system with discrete samples. But these are just ideas, so I mean, everyone is welcome. I'm happy to see this happen in the future. And with this, I say thank you. And this is kind of art and leftover from the intercomparison at the marine station was that. Thank you very much. I stop sharing now.
Thank you so much, Tobias. That was a very fascinating tour of the different aspects of the intercomparison that you've led. So I think that was very insightful. I don't see any questions yet, but maybe I can maybe start off by asking, did you find anything interesting or unexpected from the results that you've seen so far from the comparison?
Well, unexpected always means that you never thought about that. Maybe not that. I think maybe what was unexpected that it was very clear the differentiation between the equilibrator, the water equilibrator-based systems and the membrane-based systems. I think there was speculation in the community, but you had good studies or not that good studies, and here we had everything at the same place. And the plots that I showed, the difference plots, we didn't do much massaging, right? I mean, we did the groups did the data processing, we did put the data together, and we produced the plots, and basically the picture fell very clear in front of you. Maybe so. I found this very exciting and maybe also a little bit unexpected that it's so clear the picture because the groups look like someone massaged it that they look like they look, but this did not happen.
Very nice, yeah. And I know you mentioned that there's been a bit of change in the flagging of how the data is, or the data flag, I think it's how it's called in the SOCAT now.
Yeah.
But other than that, has this led to some sort of change in calibration?
I mean, I hope that the people pay more attention now to their to their sensors that they have at the instrument. Of course, no one tells me what they do change and what not. Therefore, we can just hope that it happens. But the measure that I have is that companies talk to us and said, "Hey, that's very interesting. We wanna get better. Can we work together towards ideas how to improve the system?" And this did not, of course, land only on my table. I guess there are other collaborations between groups and manufacturers where I know that they use this outcome to sit together and improve the instrument of interest. So I guess for us,
Thank you.
for us as a community, this is the real power also coming out of it, right? That also the manufacturers take it home and work on it.
Indeed, indeed. It's definitely a very insightful study. And I think that's the same comment that Hannele has shared here. So she says, thank you for the excellent and clear presentation. And it's a very impactful study. I don't see any questions or any hands. Yes. Please go ahead.
Hello, everyone. I'm Alessandro Laudicella from OGS, and thank you, Tobias, for the presentation. Can you all hear me?
Yes, perfect.
I have a question regarding the experiment. It's really interesting, and I think it's when you show the plot with the salinity, temperature, and air temperature, water temperature, there were also some fluctuation in the salinity range. And I was wondering if that was because you used the seawater or you just changed it artificially, the salinity.
No, the salinity at this day we changed the water completely. So we had to drain the tank because it looked like some biofilm was starting to form on the surface. We were discussing it shortly, and then we decided to just drain the tank. We cleaned the tank and then refilled it. So it was a tank truck that came with new water, and since it was natural seawater in the North Sea, you can't. Apparently, that's the variability in front of the Belgium coast.
And that's very interesting. And have you seen that an effect of the between the two different old water and new water to different salinity. There was also different in pCO2 readings from the instruments.
Yeah, no, I mean we didn't see a different response, but we all
Okay.
know. I mean, so the salinity doesn't have a big impact on the pCO2 directly, and since we used, I mean, we used only pCO2 instruments, right? We didn't use instruments that were calculating the pCO2.
Yeah.
Maybe the instruments that get mostly impacted from that were instruments like, for example, the SAMI systems where you have first diffusion through a membrane into an internal liquid that changes the pH, and then you measure the pCO2. For classical membrane systems, I think this switch didn't matter that much.
Thank you.
Thank you, Tobias. I don't see any more hands or any questions. So I want to thank you and all the people who have participated today. And so thank you for joining in the ICOS talk. And thank you, Tobias, for this very insightful presentation. And we look forward to hearing more from you.